Good morning. Welcome to Process Injection Techniques Gotta Catch Them All in South Seas CDF with Itzik Kotler and Amit Klein. Before we begin, I have a few brief notes. Stop by the business hall located in Mandalay Bay, Oceanside, and Shoreline ballrooms on level 2 during the day, and for the welcome reception at 5:30 p.m. tonight. The Blackhead Arsenal is in the business hall on level 2. Lunch will be served in Bayside AB from 1 p.m. until 2:30 p.m. Don't forget the merchandise store on level 2 as well. And thank you for putting your phones on vibrate. We're ready to get started.
Thank you.
Thank you, Lena, and welcome to our presentation about process injection techniques. And we have Itzik Kotler here, and this is some words about Itzik. And my name is Amit Klein, and you can read a bit about me there. And we started researching process injection techniques back in late 2018. We wanted to explore this area and to see if we can find new techniques and something interesting to say about this. And pretty soon we discovered that there's actually no comprehensive collection or catalog or compendium of process injection techniques. Moreover, there was no separation of what we call a true process injection techniques from a more liberal approach taken by some authors to this term, wherein they lumped into process injection some related but not true process injection techniques like process hollowing or spawning. We did not find any categorization system for describing the differences between the sub-techniques such as memory allocation, memory writing, and code execution. There was no analysis and comparison between the various techniques out there. And there was no update for Windows 10, as several techniques are pretty old from the Windows XP days and the 32-bit architecture. And it was not clear to us whether they can be ported as is to Windows 10 with its new security mechanisms and the 64-bit architecture. Before we proceed, let me do some kudos and give some kudos to the individuals and companies for inventing and developing, documenting, and providing proof of concept to many process injection techniques. Among them are Adam of Hexacorn, Odjan, the people at Ensilo, and Xaba Fitzel, also known as the EvilBit, and there are, of course, many more authors and contributors. And of course, hat tip to Endgame for providing the first compilation of injection techniques, although not all of them were true process injection techniques. So how do we define true process injection? It's injecting code or logic from one live user space process, which is typically malware, to another live user space process, which the target of the injection, which is typically a benign or a legitimate process. This is in contrast to process spawning and hollowing, also some other pre-execution techniques like DLL hijacking, APP-cert, APP-init, LSP providers, image file execution options, etc. What's so interesting about Windows 10 and the 64-bit architecture? Well, in Windows 10, there were several new security mechanisms introduced to mitigate remote process exploitation, but they also have a significant impact on process injection, on local process injection. Specifically, CFG, Control Flow Guard, prevents indirect calls to non-approved addresses, and the CIG, the Code Integrity Guard, only allows modules or DLLs signed by Microsoft or Microsoft Store or WHQL to be loaded into the process memory, and we will explain exactly how this affects process injection. The x64 architecture, as opposed to x86, the 32-bit architecture, has a different calling convention, wherein the first 4 arguments are stored in volatile registers R6, RDX, R8, and R9. So invoking functions, for example, from a ROP gadget or from other mechanisms, necessitates control over some or all these registers, which is sometimes hard to come by. Also, in x64, there is no pop all registers, so this makes it difficult to populate registers with desired values in ROP gadgets and so forth. We found a lot of proof of concepts for process injection out there. They were excellent proof of concepts in the sense that they were not just good proof of concepts, they were excellent ones. And they were excellent ones because they checked for error conditions and exceptions. They handled both 32-bit architecture and 64-bit architecture. In fact, when they wanted to demonstrate a specific, say, memory writing technique, they coupled it with some execution technique to provide an end-to-end process injection demonstration, including, in this case, an arbitrary, executing arbitrary code, a user-chosen arbitrary code. This made a proof of concept pretty large. In this case, if you can read it, it's 1,500 lines of code. And for a researcher to try to figure out what exactly is the innovation here, what is the essence of the technique, it becomes very difficult, as opposed to what we had in mind is something like the right-hand side, where there are 3 lines actually. They show up as 5 because we have a word wrapping here, detailing the exact writing technique. And that's what we're missing in the proof of concept or in the discussions that existed to date. So the scope of our research is therefore true process injection, running a sequence of logical commands in the target process as opposed to making the target process spawn another process, which is far less interesting. Recent Windows 10, let's say version 1803 and above, 64-bit injecting process, 64-bit target process, both medium integrity, no requirement for administrative rights. And we wanted to evaluate the process injection techniques against Windows 10 protection, specifically CFG and CIG. With respect to CFG, what we had in mind, or what we discovered, that there are 3 strategies for handling CFG. Either the attacker, the malware, disables CFG in the target process, which is possible through a standard Windows API set process valid call targets. However, if you think about it, this invocation is in itself quite suspicious for one process to inflict on another. And also, it may be disabled or restricted in the future by Microsoft because it may be too potent. And then we can allocate or set the executable memory, thereby making all the allocation CFG valid. This is done using virtual alloc-EX, virtual protect-EX, and others. However, what we have here is one process allocating executable pages in another process, and we all understand what's going to happen next. So this is extremely suspicious activity. So an attacker probably wants to avoid that one as well, which leaves us with the third option, which is the most difficult and and hardest to come by, and therefore most interesting, which is playing by the rules. So what the attacker needs to do is write a non-executable data, typically a ROP chain, and then use some CFG agnostic execution method to run a stack pivot and start executing the ROP gadget. And the emphasis is on CFG agnostic execution method, which is a rare minority of the execution methods, as we'll see later. Regarding other defenses, including CIG, they could be turned off by invoking locally set process mitigation policy, which takes 3 arguments and therefore could be used with NTQ APC thread to execute at the target process. However, this, as of 1809, does not work. Among those protection mechanisms, CIG is the most painful for process injection because it prevents loading of arbitrary DLLs. So what are the typical process injection building blocks? We have memory allocation, which may be implicit if we use a code cave or stack or a known heap location. We need to consider page permission issues. Is it can we allocate executable pages or not? What control we have over the allocation address, and whether the addresses are CFG valid. And then we need to write something useful into that memory. And the question, and with memory writing technique, the questions are what we can write. Can we write arbitrary data, or is it restricted in size or in character set? And whether the write is atomic or not. Finally, there's the execution technique, and the questions are whether the target has to be a CFG valid address, what control do we have over the registers, and what limitations or prerequisites there are for this execution technique. And there are a lot of techniques that are quite restricted. So without much ado, let's go over to process injection techniques. I'm going to describe some known and then some interesting and lesser known techniques, and try to analyze and provide some insights about them. So we start with the classic memory allocation technique, in which we allocate memory in the target process using virtual alloc EX. As we all know, we can allocate executable pages simply by requesting the page execute property flag. And for such executable pages, Windows conveniently automatically sets all the region to be CFG valid, comes in very handy. As a variant, we can allocate only read-write pages and then add the executable flag using virtual protect EX. In that case as well, Windows automatically sets all the region to be CFG valid. And then we have the classic write process memory writing technique. With write process memory, there are no restrictions and no limitations. The address is fully controlled by us. And with CFG, if the allocation sets the execution privileges, then we know already that all the region is CFG valid, which makes us very happy. And CEG has no impact because we're not talking about DLLs here. And finally, there's the classic execution technique where using create remote thread has no prerequisites, no impact for CIG. For CFG, the target execution should be a valid CFG target, meaning Windows will check at the remote process if the address is CFG valid, and if it's not, it will crash. And as for registers, we only control a single register, RCX, so whatever we invoke here has to take up to one argument. We also have classic DLL injection execution techniques. One of them would be using create remote thread again, assuming that we already have the DLL path in memory using using a writing technique. Then we can invoke create remote thread that invokes load library A, with the single argument being a pointer to the memory that we filled with the DLL path. The prerequisites are pretty obvious. The DLL should be on disk. We need to have a writing technique to write the DLL path to the target process. Interestingly, the execution occurs because the loader runs DLL main during the loading of the DLL, and this DLL main function is restricted because it's executed under the loader lock. So there are several restrictions. There's a URL in our paper that provides information from Microsoft what those restrictions are. Nevertheless, it's still very useful. CFG has no impact on this technique because load library A is obviously a CFG valid address in the target process. However, CIG will block this technique assuming that this DLL is not signed by Microsoft, and unless you have the Microsoft code signing key, the CIG will block this execution method. I want to note that this variant there are variants using QUserAPC and NTQAPC thread which end up with the same conditions more or less. Another classic DLL injection technique is using set Windows hookx, in which case the idea here is that the malware provides Windows with a DLL to be loaded whenever a specific event is triggered in the target process. And following this set Windows hookx, we artificially trigger this condition, this event in the target thread, and so that it forces loading our DLL and executing the event handler function in this DLL. Of course, the prerequisite is that there's DLL on disk and it exports the required function, which is obviously under the attacker's control, no problems there. And again, CIG will block this technique. We are moving to the classic APC execution technique, which uses QUserAPC, the Windows API standard function, or the internal function NTQAPC thread, which is more flexible. The prerequisites here start becoming interesting because here we require that the thread must be in an alertable state, and I'll explain that in the next slide. CIG has, of course, no impact, and CFG requires that the target execution be a valid CFG target. As for registers, you can see that in QUserAPC, we only control RCX, one register, one argument function, whereas in NTQAPC thread, we control RCX, RDX, and the lower half of R8. So we have control over 2.5 registers. So what is this alertable? What does it mean for a thread to be in an alertable state? Well, taking it straight from Microsoft documentation, it means that the thread is inside one of the in idling in one of the 5 next functions: sleep ex, wait for single object ex, wait for multiple objects ex, signal object and wait, and real MSG wait for multiple objects ex. And actually, for a complex enough software like Office software, Explorer, browsers, it's quite common to find at least one thread in an alertable state. If you think about it, any thread that waits for an object, waits for a signal, actually is in an alertable state. And also of importance here, and I don't think that this is documented elsewhere, is that it's quite easy to detect this alertable, that a thread is in an alertable state, because all those internal functions in which the thread is actually parking, it will be at the function entry plus hex 14, which is the RIP right after the syscall. All those 5 internal functions share the same structure, and it's always a syscall, and at the end of the syscall, it's hex 14. So if you see the RIP for a thread in sleep ex, say, plus hex 14, or in signal object and wait plus hex 14, it means that the thread is in an alertable state. Otherwise, it is not in an alertable state. Moving to the, so that was the APC style execution, and now moving to a classic thread hijacking execution technique, suspend, inject, and resume, SIR for short. Again, the naive representation of this attack is opening the thread, suspending the thread, and then using set thread context with our RIP pointing at our desired location, and resume thread, and the thread is resumed with the RIP in our desired location, and start executing our code. Now, there are no prerequisites actually to this technique. CFG, surprisingly enough, has no impact except for RSP, which is restricted to if we choose to change the RSP value, it has to remain within the stack region. As for control over registers, here's a puzzle. In some processes, we could exert control over all registers using set thread context. In other processes, more interesting processes, I admit, we could not modify or we could not control the volatile registers, RAX, RCX, RDX, and R8 to R11. The reason why some processes are more controllable and some are less controllable is somewhat of a puzzle to me, and probably requires more research, or maybe there's something I'm missing. At any rate, our assumption is that we have no control over the volatile registers, and as I mentioned earlier, control over RSP is limited to stack reservation. If we do not have the ability to write executable code pages into the target process, we can use data there as drop chain, in which case we set the RIP of the thread to a stack pivot gadget to set the RSP to the control memory, and the return command will start executing the drop chain instead of running native code. Here's a less known but very impressive technique from, I think, 2007 called ghostwriting. It's a monolithic technique in the sense that it allows writing, it combines writing and execution. It's similar to thread hijacking, but it has the built-in memory writing part. So memory writing is achieved in steps, writing one keyword in each step, and using set thread context to set the registers. And at the end of each step, the thread is locked in an infinite loop, which is a success marker for us, telling us we can move to the next step. So the required drop gadgets are, we have a sync gadget, this infinite loop, as simple as jump -2, so it loops forever. Then we also need to have a write gadget, something like move to the address in RDI, the contents of RBX, and do a return later. And a stack pivot or something equivalent. In the first step, we just write onto the stack the address of the infinite loop and return to that so the infinite loop start running. Once we detect that, we again set the thread context to say, into writing arbitrary keywords using RDI and RBX, and setting RSP one step back so that when the write gadget will finish with return, it will jump back to the infinite loop. And once we have built the memory to our desire, we can move to the execution by executing a stack pivot using set thread context again. Some tips regarding unused stack as memory, which we can use in this technique and as well in the stack bombing technique that we'll describe in a moment. We need to maintain distance from the official top of stack. So in order to leave room for WinAPI call stack, meaning we need to allow the stack to grow a bit when some internal functions are invoked. Otherwise, if we do not do that, if we use the stack right behind TOS, it will get mangled or wiped by invoking internal functions. So no good, so need to keep some distance. We can't go too far because the stack is limited to 1 megabyte typically. So in order to achieve those goals, we need to grow the stack by touching memory at page size intervals, because if we do, once we touch this, once we touch the guard page, the stack grows accordingly. Also, when writing code, using this new stack location, mind the alignment required from stack, which is 16 bytes. So back to analyzing ghost writing, the prerequisite is simply that we have writable memory. As we can use, as hinted before, we can use the unused part of the stack. CFG has no impact except for the restriction over RSP. CIG obviously has no impact, and as for control over registers, there's no guaranteed control over volatile registers, as I mentioned before, and as I said, control over RSP is limited. Another interesting writing technique is assuming that there is a shared memory section in the target process. In such case, assuming that we know this shared memory name, shared memory section name and size, which we can easily find out assuming back at home, assuming that we know which software we target and which build it is, because these things don't change a lot. We open this shared memory, map this shared memory to the malware process. We write our payload at the end of this shared memory section. And finally, we open the target process and we search for sections that are, for memory regions that have the same properties as the shared memory in terms of size and flags. And once we find that, we read the last bytes of that memory area in the target process. We compare it to our payload, and if it's indeed the shared memory region, then we'll find a match, and what we have at hand at this moment is our payload at a known location, at a known address in the target process, and then we can proceed to do whatever we like with this data. So the prerequisites are obviously that the target process has read-write shared memory, and that the attacker knows the name and size of this shared memory. CFG is not interesting. This is a memory writing technique, and CIG has no impact. We're not dealing with DLLs here. Moving to the atom bombing writing technique. So as we saw earlier, the full proof of concept is 1,500 lines of code, but the essence of the technique, assuming some simplifications here, like let's say the payload length is smaller than 256 bytes, and assuming that there are no null bytes in the payload except the terminating null bytes, what we simply need to do in the malware process is define an atom object for Windows with this payload as the content, and then using anti-QAPC thread, which can invoke any function in the target process with up to 3 arguments, we invoke the global get atom name A. With this atom name, the target address for the payload and the size of the payload, and it will run global get atom name A in the target process, which will copy the atom data, the payload, into the desired address, which is very neat. The original paper does not write null bytes. They assume that the target memory is zeroed out because they use a code cave. And we devised the technique to write null bytes. It's all in our paper if you're interested. The prerequisites here is because we use an APC execution technique, the thread must be in an alertable state, but that's not typically a problem. And this is a writing technique, so there's no impact for CFG, and for CIG is irrelevant because it's not a DLL. And another interesting allocation plus writing technique they are lumped together in this one is forcing mapping of a section on the target process. In this case, we define a section in the malware. We fill it with our data, and then we forcefully map it into the target process using NT-map view of section, which also allocates the memory in the target section. And if we ask for page execute, it will also set the whole memory region to be CFG valid. The downside is that it cannot be used for an already allocated memory. So this one cannot be used to, say, write data on the stack. And as for CFG, as I mentioned earlier, the memory allocated with page execution privileges becomes a valid CFG target, which is very neat. And here is a cute execution technique. It's what we call unmap plus rewrite, in which we unmap a prominent DLL in the target process. Specifically, NTDLL is of course the probably ideal choice. What we need to do is to unmap this DLL and then map a section back exactly in the same size to the exact address of the original NTDLL in the target process. And so so next time whenever an NTDLL function is invoked, our own code will run. The way to do it is a bit more tricky and requires attention to details. First, of course, the whole target process needs to be suspended. Otherwise, if some thread will invoke function at NTDLL, or once NTDLL is unmapped, but before our code is there, it will obviously crash the process. Then we can't just write data there. We need to retain the context of many internal NTDLL variables. To do so, what we need to do is copy the original content of the whole NTDLL region to the malware process, then patch some functions of NTDLL like NTClose, and then write this data back to the target process instead of once we unmap the original NTDLL. Otherwise, if we don't do that, the process is very likely to crash because of inconsistencies. And of course, we need to flush the instruction cache in order to tell the CPU not to use any old code from the old NTDLL it cached. Since all the since the memory that we allocate inside the target process replaces the old NTDLL, all entry points in NTDLL, all functions in NTDLL must be CFG valid. Fortunately, if we use either virtual allocx or NTMap view of section, this is taken care of. And then there is a bunch of callback override execution techniques, what we call. I lumped together a whole lot of execution techniques, starting with set window, long PTR, propagate, control inject, ALPC, WNF, and the whole shutter-like techniques together because they share the same concept. What they do is they write the target code or logic into the target process. And then the execution revolves around finding or obtaining a memory address of an object with a virtual table, specific object or specific callback function or specific function table, which in itself may be tricky because the object may or may not be there depending on the nature of the process. For example, whether the process uses ALPC or not, whether the process is in console application or not, whether the process has a private clipboard or not. It's not a very generic approach is what I'm saying. This finding / obtaining can be done either via a standard Windows API like get window long PTR or via a memory search, which is the case for ALPC, the ALPC attack. Once this object is found, we replace the object or the callback function using one of the writing techniques or using the standard API if it applies, like set window hookx, set window long PTR, to point at our chosen function or code. This for all such techniques must be CFG valid targets. And it also, it may require some object or code adjustments in order to make the process stable and not crash. Finally, we trigger the execution. Again, this may be tricky in some techniques or some approaches as the triggering event may or may not be deterministic. And post injection, we need to restore the original object or callback. Here's an example, a very concise and simplified example. I'm using control inject as an example. The idea here is that a console application, mind you, this is now quite a restricted set of processes. A console application stores a handler for the control inject event in its kernel-based single handler variable. There's a bit of a complication here because the pointer stored there is encoded. Fortunately, we can use the function RTL encode remote pointer from within the malware process itself to encode our target code location using the encoding scheme or using the key of the target process. So once we do that, we copy this address, we copy the encoded pointer to kernel-based single handler at the target process using any memory writing technique we like. And of course, we have our code there already using any memory writing technique we like. And finally, what remains to do is for us to trigger the execution, and we do that by simulating the control C event. First, we simulate pressing control and using send input, and then we simulate pressing the C character with post message, and once that happens, this function is invoked and code starts running. Our code starts running in the target process. And now, finally, we move to our own little set of new techniques. We first describe a memory writing technique using a memset and memmove, which has some very interesting properties. What we do here is assuming that we write our data to the destination, to the target process byte by byte using memset and invoking memset in the target process using NTQAPC thread. Now remember, it can invoke a function with 3 arguments. Fortunately, memset uses exactly 3 arguments: the destination address, which we control, the 1 byte data, and the length, which for us, the interesting length is, the useful length is 1. This way, we invoke memset once and write a single byte in any desired address in the target process. We can do a loop over and write whatever we like, and write arbitrary data to arbitrary memory locations in the process, in the target process. And finally, we can make it atomic by writing the data to some temporary address not in use, temporary buffer not in use, and then copying the buffer in a single atomic step using memmove, which allows us to move using again NT-QAPC thread with memmove, taking 3 arguments: destination address, source address, and length. Thereby, we can achieve atomic memory writing. CFG, note that although we invoke NT-QAPC thread, CFG has no effect on us because the target functions, the memset and memmove, are of course CFG valid. And we can write to any address, in fact. The only prerequisite is that the thread must be in an alertable state and the memory should be allocated, which are not a serious problems. And finally, we describe here our stack bombing execution technique, which is a new execution technique. In this case, the idea is pretty simple. We are using get thread context to obtain the thread's top of stack, the thread's RSP. And if the thread is in an alertable state, I'm taking a simple example here, it means that when the thread resumes from its alertable state, as we see here, it will immediately, after the syscall, it will immediately return. There is no manipulation of the stack, there is no manipulation of registers, which is very handy. So if the target thread is in an alertable state, it means that if we now write the address of the destination code in the address of pointed by RSP, the thread will actually branch, the return in the thread will immediately branch to our own code. And that's essentially the idea. In our POC in the white paper and in Pinjecta, we will see this. We will see how we implemented this using the unused stack as an additional memory. We built the ROP gadget, and we have this the thread actually running a stack pivot into the ROP gadget and start executing our ROP gadget. And all this without resorting to allocating executable memory in the target process. The prerequisites are that the thread is in an alertable state, there's no impact over CFG, and as I mentioned, the paper in Pinjecta includes the fully functional code. We also looked at we also discovered 2 methods that no longer work. If anyone can provide us with a working example, we'll be much delighted. And to summarize, we've seen several writing techniques, actually 5 of them, and these are their properties. We've seen a lot, over 20 execution techniques, but only 4 of them are CFG agnostic: the thread execution hijacking, suspend, inject, resume, ghostwriting, unmap and override, and our own stack bombing. If you're interested in loading a DLL into the target process without writing, a system DLL without writing its name first, fortunately, we have a nice trick for you. You can use kernel base. It contains a list of over 1,000 system DLL names, including MSHTML, Shell32, and WinInet.dll. So if your favorite ROP gadget happens to be there and the DLL is not already loaded, here's a nifty way of loading your system DLL into a target process. And now I'm handing it over to Itzik.
Thank you, Amit. Okay, so as Amit mentioned, in addition to the theory that we did and the research, we're going to release a tool today called Pinjecta. Pinjecta implements all the different techniques that Amit has just detailed, as well as the stack bombing technique that we have introduced. So you can go right now to GitHub and download your copy. It's free, it's open source. Let's talk about what's the high-level structure of Pinjectra and a little bit about the philosophy of the design before it. So Pinjectra is a Visual Studio solution that contains 4 projects. As Amit mentioned, some of the attacks require DLL artifacts, so we provide those out of the box. That accounts for the first 2. And then we have the Pinjectra tool itself that contains the demo and the techniques. And for your convenience, we also included a test process, a dummy program that sometimes will also put the thread in the alertable state. As Amit mentioned, it's a prerequisite for some of the techniques. So conveniently, the program will do it for you as well. Now, stepping back a little bit about what's the philosophy behind Pinjectra. So as Amit mentioned, the research took a lot of effort collecting different scrapes and organize them together into a framework. We decided to take it to the next step, and we basically utilize C and C++ static type system to create and basically break down the concept into 2 different classes types that together can combine into a process injection execution. So how does it look like? So here is the first example of how you implement stack bombing with Pinjectra. The first class is providing the code execution. And again, this is a thread suspend inject resume, not to be confused with the other technique that Amit has presented. This is just a conceptual logic of what's going to happen. And then the second class is the actual writing to the memory. As you can see, netQAPC thread with memset. And the third class is actually the implementation of the payload. So as you can see, you can easily mix and match. You can take every different class and you can prototype existing techniques and expand them, or you can try different components. And now let's have a demo. Okay, so what do we see here? There's 2 CMDs windows. One of them is the green. That's going to be the victim. The other one's going to be the red. That's going to be the attacker process. First, we launch the task program. As you can see, it will print for your convenience the PID, TID, and put the threads into an alertable state. Then we're going to switch into Pinjectra. We're going to run it without any arguments. We're going to get the usage detail, all the different techniques and combination. Again, just a demo tool, not limiting the possibility, just common frequency combinations. And then once we choose the right combination, we enter the details of the process ID and the thread ID, and the injection will happen. The payload right now that the program is designed to run with is a simple hello world pop box that you can see that just popped here. That's essentially the completion and the visual indicator that the injection was successful. Thank you. Moving on to the second technique, as Amit mentioned, the ghostwriting. It's very exotic, very interesting to implement. As you can see, again, the first top class controlled the code execution. Second class controlled the actual writing. Here we implemented the ghostwriting technique. And then a different payload that matched together. And let's see how it works. Again, we invoke the test program. Making sure it's running. Yep. Going back into the Pinjectra, again, we will run it again just to see all the different options. Again, the payload here is a visual indication of the hello world box. Again, another successful process injection. Okay, so for the quick ones, you can see that this first class has already been used in the past. So if you look at the process suspend, inject, and resume complex, that's the same class that we use for the stack bombing. Again, the concept of the mix and match and reusable components really starts to give back at this point. Here, we only need to implement the unmap and map using a specific writer, which is a combination of the create file, map view file, unmap, and then view it again. And again, this combination, together with the payload that has been passed, specifically will result in a process injection technique. So again, this is just how easy it is to either prototype a new technique or using an existing one. Here, as Amit mentioned, it requires a program that has multiple different functionalities and complexity to actually be using it. So in this example, we're not going to actually use our test process. We're going to use Explorer process as a result. That's a quick batch script just to find out the PID of Explorer. Now we're going to attack the Explorer process in the computer. We're going to enter the PID, and then touching the taskbar will get the job done. Here it is. And last but not least, actually one before the last, we have the set window long pointer. Here again, you can see the complexity of the framework comes into play. We're using a specific code execution, and then we're using a convertible to actually reuse a very primitive writing technique, which is a combination of virtual allocate and write process together with a payload. And that's all combined nicely into this one huge instance of a class. And then invoking it with the inject method at the bottom will get the job done. So here's a quick demo. It's important to note that since, as Amit explained, there's a specific structure that requires to be retrieved and changed. In this particular case, we're not using a task process. The actual Pinjectra does the location of the PID and retrieves the relevant struct for you. So this is going to be all Pinjectra doing 00 indicating no actual process ID needs to be specified. And last but not least, it's the atomic bombing implementation in Pinjectra. Here again, you can see the QUser APC being the code execution class, and then a combination of open thread, open process, virtual allocation, and global add atom to complete the actual writing. And as you can see, you can control the payload, the different flags, and you can experiment with different variation. Again, we will be using the Explorer as a test process. And here it is. Excellent. Well, that will be the last demo of the day. Amit, back to you.
Thank you, Itzik. So to summarize, what we have here is a map of the vast territory of true process injection, and we provide an analysis and comparison in a single collection and repository available in our GitHub. We also provide, of course, the library, Pinjectra, for the mix and match generation of process injection attacks, which is mighty important because this mix and match allows us to cover various combinations that are not provided in POCs today. And we describe a new CFG agnostic execution technique, the stack bombing technique, and a memory writing technique coupled with it based on memset and memmove over APC. Thank you very much. I believe we have time for a few questions. You can
just step up to the microphone.
Yes, step up to the microphone, please. Okay, thank you very much.